GLM 5.2 is a 744 billion parameter model. To load this model itself, you might need room full of servers and you have to spend tens and thousands of dollars to just load this model. But recently I found an repository where somebody tried to load this model in a normal laptop system with 25 gigabytes of RAM. So today we are going to explore how he made it possible to make this particular 744 billion model in a single laptop with 25 GB RAM. So like I said, GLM 5.2 is a 744 billion parameter model. Even if you consider a half a byte for each parameter, that's still 744 billion parameter. That almost equal to 250 GB of graphics memory that you have to require. And to be frank, this cannot stay outside a particular server room. You cannot have this 250 GB RAM inside your laptop at least. At least mine definitely does not have that. That's where this particular methodology or this particular repository hit my nerve, because this repository, rightly named Colibri, which means hummingbird, that means a tiny, uh, that means tiny itself, managed to run this particular repository without using any graphics memory at all, and using RAM and the hard disk to store this particular weights to run this model without using a graphics card. And let's see how he or how this repository achieves to do so. To understand how this particular model works with just using the RAM and the hard disk, you need to understand the architecture of this particular model called GLM 5.2. So basically this 744 billion parameter model is an MOE model. So what is MOE? The direct example that I can correlate this particular concept into a real life world is by using a library. So when you come into a library, you have lots of books, but you don't know how to achieve or get those books for your requirement. That's where we have a specialist there called a librarian. So we ask the librarian our requirements and he will pick the best books that is available in that particular library out of all the thousands of books that is available there. So that is the basic concept of a router and an MOE that is being used in GLM 5.2. So out of the 744 billion parameter, we only need to use this 40 billion parameter to select, or 40 billion or 8 experts at a time, that is almost equal to 40 GB of the data to load the experts. And we are using a specialist expert to select which experts are being selected, and that reduces the whole 355 GB to just over 40 GB, and that's a huge gain. How he manages to load, that is the first step of the huge gain, where he manages to load this particular model in a simple hardware using RAM and the hard disk. So when I said that out of 744 billion, only 40 billion active parameters are there, these 40 billions are not static. Each experts could change for the upcoming tokens. So basically, when a token or a word comes in, the expert might change for each context that it gives. So how do we store this 144 billion parameter? Actually, even though this 40 billion is the only active one, we need to store this 744 billion parameter in the same device. And loading them into the RAM or the memory of this device is going to be also costly. That's where this particular repository uses the hard disk to store this 744 billion parameter. So basically, all of us might have an SSD or a hard disk where you have 500 GB of space. So all of these 744 billion parameters are stored in the hard disk, and out of which only 40 billion parameters are loaded at a time based on the tokens. And selecting those 40 billion parameter is also really complicated, because loading that at a time is going to be really slow, because you have to select 40 billion parameter each time a token comes into the picture. So that's where things get more interesting. So out of this 40 billion parameter, only 11 billion parameter changes, and that change other 29 of them are kept intact. So those 29 GB or 29 GB of data should be always kept in the RAM, and other 11 billion parameters will change at a time. So for selecting the model or so selecting the expert, there are few criteria. You don't need to update the criteria or the experts for each token that comes into the picture. So for example, you are a person, you have some inclination to some topics, or when you go to a library you might have some inclinations to topics based on the projects you work on, the technologies you learn, or the stuff you want to work on. So basically you come to the librarian and you ask the you say your requirement, and the librarian fetches the book for you. So here is the fetch part comes in, because after a couple of iterations, the librarian might know what operations or what project you are working on, and he might or he can point you to the right experts at a time. So that's where this 40 billion or most of these 40 billion parameter becomes static, because the frequency at which you learn or you try to pick up a subject, this particular router or the expert librarian will fetch what are your needs and points you to the right 40 billion parameters, and these will become static over the time. And when a new topic is approached or updated, it will have some importance compared to the other points, but still frequency tops the recency part, and that is achieved in the code based on the points that is given for the recency as well as the frequency. For example, recency is given a point of 255 bits, and frequency is given a point of 256 bits. So recency is capped 1 bit below the frequency. The other point is that you don't want to change the experts very frequently. How is that made possible here in this particular MOE is that you have kept a threshold of 25%, 25 plus 4%, so that there is a certain amount of certainty that the upcoming or the recent selected expert is much more better or are certainly better than the current selected experts. That's only when the selected MOE experts change. So that's how the architecture of GLM basically works. So basically when I mentioned that there is like 40 GB memory that is being loaded to the system, it's still way larger than the 25 GB RAM that is available in your particular system. So in order to achieve that kind of strength or the level of memory compression, basically we are using an Int4 compressed or quantized version of this model. But that doesn't mean that the quality of the results of this particular model is being compromised. Basically, from the experience that was shared by the people in the community, this particular method, when they tried in their system, which is obviously 25 GB of RAM, this particular model tends to be performing on par with the float 32 or float 16 model that is available, and it is exactly matching the output token per token. It's almost identically. So these are the few metrics or the methodology how this particular model is being loaded into a system without using a GPU and using only the cache memory as well as the hard disk. So the earlier version of the model, when you try to load this particular model to your particular hardware, it is noted that this model just scrolls at the beginning. That's where the fine tuning or the MOE starts learning your habits. So once it starts learning and achieve its full on extension of learning, this particular model becomes much more faster. And I had to be frank, even though we loaded this model, you cannot expect it to run really fast. However, you run in a high-end GPU. This was a start. This is a start. It's actually an experiment to load 744 billion parameter model to a 25 GB RAM. So this is a start, to be frank. This is how we start to move or shift the gear from a high-end GPU where millions of dollars are being spent by major companies like Nvidia, Tenstorrent, and other, who are spending on a lot of money on top of this technology, as well as leveraging them by selling them to companies and us. So this particular leverage is being held by the major institutions, can be reverted back to us by using smart techniques by like this. So this is an eye opener for all of us. I think we should try and look at other models where we can try these kind of things and start to load this model or smaller models into our system, so that we might be able to fine tune the model to load on a similar hard disk or a hardware in the future. So that's where this particular model or this particular methodology is pointing to. So basically, by end of this video, I think you might have figured out the architecture of a GLM model, what an MOE is, how this particular feat of loading 744 billion parameter model to 25 GB of an machine in a RAM was made possible. So don't take my word for this. I think you should explore this particular repository called Colibri and try it on yourself if you have 25 GB of RAM, of course. But since I don't have one, I am just went through the concepts behind it and just explaining it as of now. I think you should explore it if you have the memory with you. And if you want to learn or look into more of this kind of stuff, I definitely think you should subscribe to the channel. And also, if you like this video, you should definitely like it.